We left off talking about balancing chemical equations and how if we have a balanced chemical equation, that the type and number of each element on each side will be the same. So on this example, we have 4 hydrogen atoms on one side and 4 hydrogen atoms on the other, and we have 2 oxygen atoms and 2 oxygen atoms. Now, this is a balanced chemical equation, and the reason we care about that is that we can't compare different reactions, different sides of the reactions, without looking at how the reactions are balanced. So for every 1 oxygen that you start with, again, there's an implied 1 here, 1 oxygen you start with, that would produce 2 water molecules, assuming complete reaction. This ratio is what we call stoichiometry. Stoichiometry is the measurement of atoms, counting atoms in a chemical reaction. And we can use this relationship in even more complex reactions. This is that microscopic picture. 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 water molecules. But even at the large scale, this 2-to-1 atom ratio would be preserved. But if we look at this, we see that O2 weighs substantially more than hydrogen. You'll find that oxygen weighs almost 16 times as much as hydrogen. So that if you were to weigh out the hydrogen reacting with 1 equivalent of oxygen, you would find that the hydrogen weighs substantially less than the oxygen. So this molecular picture, we need to also worry about the much larger macroscopic picture. And for this, we need to do a much larger relationship than individual molecules. This is where the mole comes in. Right? Reactions take place between molecules, so that's Dalton's law. Unfortunately, this molecule-to-molecule reaction system that we've developed in the balanced chemical equation needs to be represented at a much larger scale. And for this, we introduce the concept of the mole. Now, the mole is best thought as a surrogate for the molecule. It's a proportional amount. The analogy I use is wheels on a car. If you have 1 car, it'll give you 4 wheels. If you have a dozen cars, it'll be 4 dozen wheels. Right? So the use of the dozen as a counting number is just as a surrogate for 1 to 4 in the case of the wheels. So the ratio between the dozens in that case is still 1 to 4. The mole is no different. The mole is just a counting number associated with molecules. And it's all moles contain the same number of units. So what this means is we can substitute in the term mole when we're dealing with macroscopic quantities. 1 mole of a compound contains exactly the same number of particles as any other mole of a compound. The reason for this is the mole is defined as the number associated with the number of particles in exactly 12 grams of carbon-12. What this does is it pegs the mass in grams, 1 gram, to the atomic mass unit, that unit we were using when we were dealing with individual atoms. And so they become proportional. So if you had something that weighed 3 AMU, a mole of it would weigh 3 grams. So it's a counting number. What exactly it is, we'll put it into play in a bit. we'll define what that number is. But for now, most of the time, we don't really care what the number is. What's more important is that 1 mole of a compound weighs the same as the molecular mass of that compound in grams. What do I mean by that? So if we go to the periodic table, pull out your handy dandy periodic table, and you look at gold, Au, we know that 1 mole of gold is equivalent to 196.96 and some change grams of gold. Why? Because 1 mole of a compound is the same as the molecular mass. The atomic mass is placed on the periodic table under the atom. That is the amount, the weight of one atom, or the average weight of one atom, or now in this case, the average weight of 1 mole. Right. So we can now use that to weigh out quantities of compounds. We can bring in this concept of atomic mass and molecular mass, the mass of a compound. We've already looked at this. Remember our dime example? We wanted to know how much one set of coins weighed. Go back and we can look at that. All right. One set of coins, all we had to do was weigh out the individual coins that make up the set, and we could figure out what one set is. It's no different with molecules. If we know the individual components, NaCl, we can look up on the periodic table and see that 1 sodium atom weighs 22.989 grams. It's equivalent to 1 mole of sodium. And 1 mole of chlorine is equivalent to 35.4527 grams of sodium. And if we total those two up, we get 58.44 and some change grams. How far to carry out? It usually depends on the number of sig figs in your problem. I like 2 or 3 past the decimal point. It's more than sufficient for most calculations. So, this means that the total mass of 1 NaCl molecule would be 58.44 AMU, but 1 mole of NaCl would be equal to 58.4 grams of NaCl. What this does is allow us to convert from grams of any compound into the mole of that compound using the molecular weight. Now, you should be able to calculate the molecular weight for anything given a formula. Relatively trivial. Add up the components. Not a very common thing that I'm going to be asking you to do. All right? But it shows up in a lot of the homework problems. You will probably be given 1 question on the test. That's about it. That has where you're actually going to be doing that. You will be using it all the time, though. So be prepared to calculate molecular weights as needed. Oftentimes I will give them to you, but not always. We now have 2 different ways of relating compounds. We now have a gram to mole relationship, but there's also a mole to mole relationship. If we look relating 2 different chemical quantities, going back to our chemical equation. If we take a look at this balanced chemical reaction below, we see that we have this 11 oxygen. We have 11 oxygen here producing 8 CO2. There's a relationship between oxygen and CO2. 11 to 8. And it's going to be consistent. That's a mole-to-mole relationship. Whenever we deal with changing one chemical entity into another, it's a mole-to-mole relationship. So these 2 relationships are central to our calculation. So let's take a look at a series of chemical reactions. What is the molecular weight of water? The weight of one molecule of water. We know it's composed of 2 hydrogens, 1 oxygen, and so you should get a number pretty close to. You run through the calculation. should get a value of 18.01 grams. It's equal to grams of water. It's equal to 1 mole of water. We can do the same calculation for a bunch of other compounds like C8H12 and O2. Feel free to run through those calculations. They'll come in handy. Well, go ahead. So using our addition skills, we can come up with these values. This relates the mass of C8H12 and the mass of oxygen to a mole of oxygen, a mole of C8H12. You go into the lab, you weigh out 31.898, roughly 32 grams of O2, you have a mole of O2. You know that. Now, let's take a look. If you were to combust 25 grams C8H12, they want to know how much is consumed in moles. Gram to mole conversion, the same thing. That's very similar. Grams of X to moles of X using the molecular weight of the compound, which we happen to have right here. Oops, not there. We happen to have right here. We can then take this 25 grams, and then we know using this molecular weight that for every 108.09 grams of C8H12, that is equivalent to 1 mole of C8H12. I know you're saying, Dan, why can't I just divide by 108.9 and I'd get the right answer? That's true, but part of this is keeping track of our units, and this allows us to convert our units away quite effectively. Grams of C8H12 being converted away into moles.
Says we have about 1/4 of a mole.
Says that there's 0.23, 3 sig figs in our problem, 3 sig figs in our answer, moles of C8H12 were consumed. Well, how about the moles of oxygen? How do we figure out how many moles of oxygen were consumed? Now, it's not 1 to 1. We know that for every 1 C8H12, that's 11 O2. Your choices are twofold. You can just use the answer that you just generated, or you can start from scratch. My suggestion is, whenever you approach a chemical problem, start with what's given. Take shortcuts later. We have 25 grams C8H12. And so our strategy, notice how this is different. We want to know moles of O2. We don't have a direct relationship. So we're going to convert our grams of C8H12 into moles of C8H12, and then convert that right into moles of O2. For every 108.09 grams of C8H12, it's equivalent to 1 mole of C8H12. For every, now we have moles of C8H12, but we can use the mole-to-mole relationship in the equation. This comes from our balanced chemical equation, which says that for every 1 C8H12, that is equivalent to, that is equivalent to 11 moles of oxygen. This gives us an answer in moles of oxygen, which just happens to be what we're looking for. 25 divided by 108.09, 25.0 times 11 is equal to 2.5. 4, 3 sig figs in the answer, C8 moles of O2 released. Now lastly, they're asking us how many grams of water. This problem starts with a gram to mole, grams of C8H12 being converted into moles of C8H12. Again, using our formula. And then we use our equation, just like to relate C8H12 to moles of CO2, water, moles of water. We use our moles of H2O to relate to the grams of H2O using the molecular weight of water. So molecular weight calculations, equation, and then the stoichiometry. So what does that look like? Again, starting with our 25 grams of C8H12. We know that for whatever 108.09 grams of C8H12, 1 mole of C8H12. In this case, for every 1 mole C8H12, that is equivalent to 6 moles of water. Again, that comes right from our chemical equation, where this comes straight from our molecular weight statement. And then for every 1 mole of water, that is equivalent to 18.01 grams of water. Again, from a molecular weight statement, but in this case, the molecular weight of water. So 24.99 grams of water are produced. Now, it turns out that it's almost exactly 25 grams, or 25 grams, 25.0 based upon sig figs. So we start with 25 grams of C8H12, we end up with 25 grams of water. All right. So, but the number of moles of water has changed. If you stop the calculation halfway through, you'll see that you get 1.4 moles of water come out. So, even though you have only a quarter of a mole of C8 being consumed, you generate 1.4 moles. But you'll see that 1.4 divided by 0.231 is a 6-to-1 ratio. Exactly what it says in the stoichiometry. All right. So, even though the mass, in this case, turns out to be the same, just by bad luck, you can still see the mole-to-mole relationship is preserved. This type of calculation, which at its most generic, you could write as ultimately grams of X going to grams of Y, is really central. We have this gram of X, we're converting that into moles of X using our molecular weight. And then there's a mole to X, mole to Y conversion halfway through. This is the stoichiometry using the equation. This is the chemistry right here. And lastly, a molecular weight statement that converts moles of Y back into grams of Y. Now, we usually can't go directly. This is usually not something we can go directly. So we have to go through a different route. This is really the central, most straightforward method that you're going to see. It shows up in almost every single chemical problem. Now, sometimes you stop at various points along this depending on what you're looking for. Now, here's one of the secrets about chemistry. A lot of chemistry is geared towards finding the number of moles of reagent so that we can do this mole-to-mole conversion. You will see this over and over again, and we're going to come back to this. So how do we actually do it? Well, using the grams of X, we know that after the molecular weight for grams of X, that will allow us to figure out the number of moles of X, because the molecular weight is defined as 1 mole. 1 mole of X is equal to the molecular weight of X in grams. Once we have that, we can use the chemical equation that says a certain number of moles of Y, moles of X, is equivalent to a certain number of moles of Y. Again, these come from the equation, the balanced chemical equation. And then we convert our moles of Y back into grams of Y using the molecular weight. To give us our answer in grams of Y. So this is one of the central methods for dealing with equations. Now, it's very easy to just pick a number and start running through this crank, but read the problem. Make sure you're actually answering that or looking for that. Good strategy on many cases is to push things into the mole and then stop and look and start to do some analysis. So to do that, you don't actually go this far. You don't actually get this far into the equation. You don't convert everything into grams. So this is a lot of the starting points for many of the chemical reactions. Now, for this to work, you have to be in grams. So you may have to convert, find other ways of getting there. So lots of good problems like that in the book.